coloqué ahí en el... Gracias. Acá está el micrófono y acá está el... Este tiene... Y aquí tiene el micrófono. Si no podés colocar este otro micrófono así. No puedo. Como quieras.
Chegou, alcançou. Tá bem? Pegou o ônibus? Aí pegava o negócio? Eu queria que fosse, né? Quer que seja. Acho que eu peguei outro slide, né? Esqueci de apagar o mês. O mês do ano tá certo? Eu já não enxergo mais nada de noite. Eu não posso mirar a distância. Se fosse lá segunda, eu estava preocupado. Agora estou contente. O tempo está sobrando.
No te quiero ninguna parte. Solo de paseo.
O tempo está 11h30, perto de Shopping Morumbi. É a cerca com 6 quilômetros, mas aqui em São Paulo, 6 quilômetros nunca se sabe. Eu esqueci lá. Embaraçado não, como se fala? Embaraçado é grave. esse outro acho que eu tenho uns 15 em casa, né? Carregador normal. Aí você vai acumulando, né? Comprando, aí agora eu troquei e aí não serve pra nada. Tem um balde cheio de cabos e pendura muito fora.
Faz parte.
Várias vezes já esquecia na estrada, eu parava e comprava. Não tanto de hidrologia. Hidrologia é um pouco mais simples.
Santiago? Vamos?
Não, mas deixa eu chamar.
Põe no bolso. Já está ligado.
Presente.
Hello, good morning everyone. So let's start. We will start with Santiago. So welcome.
Well, good morning, everybody. Today I'm going to present the impacts of the biocorrection over applied for crop simulations. The idea is to see how, if you use the model as it is, with some bias, some deviation, can impact your application. Well, just a brief results about what could be the impact of climate change for Brazil. This is the 76 RCP 80.5. This is the median for Brazil. This is the impact for the average air temperature. And you can see here for precipitation, whenever we don't see, this means that we don't have agreements between the global climate projections. So basically you can see here that even though for temperature we have impact over all and all in the same directions, for precipitation we have some disagreement between the models. Even though we have this disagreement in precipitation, sometimes when you apply for another application, the next one is see the water depth anomaly. You can see here that most of models shows in the same direction. That means that even though we have uncertainty in precipitation, this uncertainty is less than the evapotranspiration demands. So in this kind of sometimes when you apply all the models give the same direction. Okay, this is just to present just a brief about some impacts here in Brazil. And we're going to apply, I'm working at Embrapa, I'm sorry, didn't present myself. And we work mostly with crops, crop insurance, the impacts, crop breeding programs, development of new cultivars. So as you can see here, we saw in the last slide, we can see that sometimes when we applied for a nonlinear model, we can see that they can change the results. And crops, of course, it's extremely nonlinear system. We have many interactions with photosynthesis, growth, development. It depends on a lot of environmental conditions,
The water depth also depends non-linear about the soil water content, precipitation. So the idea is that I'm going to show that if you don't correct the bias, we can have very different results. Just a little brief about the impact. What could be the impact of climate change for crop production? This is for the 5 most important grain crops in the world. This compilation of more than 1,100 experiments. You can see that even though for the period more closer, we have some region in the globe that will have increase here in the blue and some decrease. But along the century, you can see that most of parts of the world is going to experience a decrease of yields in the future. So the goal is present the climate simulation systematic errors using RegCM 5 outputs from Rose, and see what could be the impact for the scenario food productions. And as a case example, we're going to apply for soybean at south of Brazil. So this is the comparing with the weather stations. This is the bias for the RegCM 4 with hard rain for the present. You can see here that the mean temperature have a deviation higher than 3 degrees. For the maximum temperature, even higher. Minimum have some place that will have a negative bias, but for maximum temperature, all its temperature is high in the model. This is the deviation for precipitation, 2 millimeters per day in some regions negatives. And for global solar radiation incident at the surface, that is very important for crop growth. You can see here that model overestimates around 2 megajoules per square meter per day. So at the end of the day, what is the impact of crop yield simulations? This is we're simulating the yields here for soybean. You can see here the scale, but here is like 5, here like between 3 and 4, okay? This one I run with the observations. This one I run with the RegCM 4 for the base period. So we can see here there is a lot of difference. Some regions pretty high, and some regions lower than when we run with the observations. Okay, more or less in scale of percentage, we have some regions with 45% of difference between 2 simulations. Oh, so and then I'm going to show 4 methods that we apply for the bias correction remove. Okay, so basically we run the model with no handling for bias corrections. That this is not the reg. This is all the CMIP 5 simulations. Okay, you can see here this is just an example. Okay, this is just from one point with the station. The weather station is over here. Okay. And this is all the models. This is the median, the 75, then at 25% of the median. We can see here that they have a lot of deviation. Okay, from one counting scale, for instance, there is really a lot of deviation. And this is very important because, for instance, for rice have the problem of sterility. Whenever temperature gets higher than 35 degrees, they have a total sterility. So if you, for instance, use this model here, in the middle of the center, basically all the years will be impossible to plant in rice at south of Brazil. So it makes a lot of difference if you use the model correct, okay? So it's just an example without don't remove the bias. Another way to deal with that is probably mostly used in Brazil, I don't know, in the other place, many people use the name delta method. The delta method basically you take the anomaly for the present with the model, with the future in the model. You see how much, for instance, if it's going too high 4 degrees, then you apply this 4 degrees for your past time series. Basically use the weather station time series, the same weather, just displace for instance, the temperature, 4 degrees, and if for precipitation and solar radiation, use a factor, how much percent is going to increase or decrease, okay? This is just example here. This is some days. This is a time series. Then this is a time series for the future. Just a displacement of the delta. That's the same of displacement between the average, the climatology for the present and the climatology for the period. This means that you don't need to use any bias correction because we are comparing with, we assume that the deviation is the same in the present as it will be in the future. The problem, the only limitation here is that you don't use, for instance, you use just the average change. If the model changes, for instance, the variability, the internal variability, you don't going to capture that kind of variation that maybe can be predicted by the models. Another way to do that is through bias correction. So here you see the same time series for that I show you without correction, and this looks like after you do the correction. Okay. So basically, you bring all this time series for all the models to the same average as you have for the all points that you have observations. So it looks more like that. Okay, you see here the present, the median is about the present. You have a lot of variability. The advantage of doing that, as I said before, that you can still keeping the internal variability change. If you change the frequency or change the streams, then you could capture in your simulation. And the last one that I've applied is the quantile mapping. The quantile mapping basically you take the distribution. Okay, this is one example, an empirical distribution for maximum temperature. This is the observed. Okay, this is how it's distribution in the model originally. So basically, you take this one relation with distribution with this one. So basically, and whenever you get the model with a value, for instance, here of 20 degrees, we means that you're going to be 22.5, for instance. Okay. Then you take this relationship for the present and you apply this relation along the simulation. Okay. So basically, this is the original model. And this is the original with a quantile correction. You can see here that to keeping the variability, but we're going to give at the end of the day with the same distribution, not on the average, but the distribution will be the same as the observation. Okay. Of course, in the future you can change the distribution, but for the present you keep the same distribution. So basically, these are the maths. Okay. And you see here the results. Okay, these are the same maps, the observed, run with original, and after we take a bias correction. Okay, this for the present. You can see here that they did a pretty good job. It's a pretty good comparative, pretty similar the observed, and after you correct the model. Okay. So what about if we run for this? This is another example also for distribution. Of course, this is the original, okay, with observed. This with the reg with original outputs. You see here a lot of spreads, even though more or less a lot of the results here. But you can see here that after bias correction and after the quantile correction, we improve a lot the spread between using the observed data set and the predicting with the model after correction. Okay, we're still having some deviation in some specific years. Probably here we have the many thousands of years, but most of annual results are very similar. What about the distribution? This is another way to see. This is how the frequency and the yields, how is the distributions for the output for the present. This is we're using the RegCM for. We can see here that we have, with the observation, we have the data, the yields are more skewed to the right, and using the model, it's more spread. Okay. This is for Paraná, Santa Catarina, and Rio Grande do Sul, some different states in the south of Brazil. And you can see here, after bias correction, we move a little bit closer to the observed distribution. This is the quantile. Of course, the quantile, you can see, if I come back, This if you just correct the average, okay, you see here, even though that there is a difference, but if you correct with a quantile, you see here that you at the end of the simulation will have a more similar distribution for the simulated yield for these three states. It's more similar, not the average, not only the average, but how the yield is distributed also for the states. So, and what about if you apply for the future? What would be the impact of the bias correction using these maths for now, not for the present, but for the future? So, this is the anomaly for the delta maths. This is the anomaly for the RegCM4 with the original. This is after bias correction. This is for the quantile correction. As you can see here, for temperature, we don't see too much difference, okay? So remember that I said in the beginning that the model is nonlinear. So basically, even though we have a similar anomaly, it depends if you correct the distribution for an application that is not linear. You sometimes have a very different result. Is that I'm going to show you. So even though I think it's best or worse with the lights? Worse, right? I don't know who turn on. Could you turn off the lights here in the front? I think, okay, I think I'm sorry. I'm sorry about So, and then you can see here the distribution for the present and for the future, okay? This is with the delta math. This is with the original RegCM4, how the temperature will be distribution in the future. And this is with the bias correction. So basically you can see here, for instance, with the original and with the quantile correction, there is some difference. Even though here you can get the same average, how temperature is distributed along the season is different, okay? You can see clear here. So this is for precipitation anomaly. Precipitation, it's similar also, but not so similar. Depends on the math of delta. You can see here some regions here, the scale is between -10 and 10%. So basically don't have too much difference. This increase of 30 to 45%, okay? You can see here some difference for precipitation, depends of the method of use. If you use just the model or if you do bias correction, it's similar, but the most different with the delta math. Actually, for this application, the most different results was when I apply the delta math. Even more different than using just the original model. Again, the distribution is another history. Even though the average is more or less similar, the anomaly, but I will have some difference in the distribution. Here you can see more closer. This is the total amount. This is more or less 400, 1,400. Okay, this is along the season, crop season. Total amount of precipitation along the crop season. You see here also difference between the distribution. This is solar radiation. Solar radiation have more or less similar results as for precipitation. We don't have exactly the same results, but even though more or less the same results, the same results for the delta maths, you see here many difference in the maps. Solar radiation is very important for crops. So it makes, for instance, a 20% or 25% make a lot of difference in the yield, the final yield. You can see here some difference in the maps, okay? See here that, for instance, you have between -10 and 10, and here you have a positive anomaly using the delta math. And also the distribution is not exactly the same. You see here the original, it's a very different distribution when you use the quantile correction, okay? So even though we don't have too much anomaly for the future, but the input that you give to the model is very different, the amount of solar radiation. Depends on the way they use. So this makes difference in the results. So then this is the impact in the final yield, okay? This is the final map, how the future related to the present is the anomaly of the yield. Whenever you see these colors here, red and orange, it's negative. Whenever green, it's more or less minus 10 and 10%, not too much difference. And blue means a positive difference, okay? And a dark green also a positive difference. The first thing you see here that the delta matrix again gives a very different scenario with the other one. I'm talk a lot about the delta matrix because here in Brazil a lot of people use that matrix. It's one of the most used for people that work with crops because it's easy to do and easy to ask Jose, okay, and you pass me the table with the delta. Jose calculates the anomaly and pass the delta, and then they apply for the time series. But you can see here that they gives a very different scenario. We have with all the bias correction that I applied, they have a very similar results. You can see here that they are very similar. We have some difference with the original model, but less than with when I applied the delta matrix. Okay. This the impacts about the standard deviation. How we have a more deviation in the future. Not because for crops, not important only is the average, but how much it's oscillating between years. Okay. Here you can see here the same. Blue is positive, red is negative. So we can see here actually it's not positive results because we are going to increase the standard deviation. That means the internal variability is going to be high in the future, okay? Again, you can see here more consistency between the maths, some deviation, but more consistent than the delta maths. For instance, delta maths means that it's going to increase, and the others means that all three results for the half south of Rio Grande do Sul shows that we have going to decrease the internal variability of the yield, okay? This is about the distribution, the impacts of the contour correction in the model. This is the yield, how the yield is going to be distributed in the present and the future. And you see here that it's pretty clear the difference between the maths. You see with the contour corrections, the distributions, it's more skewed and more closed. And here you have much more deviation. You can see here that a lot of lower yields. For instance, here is 4, here is 2. More or less, less than 2 is probably total loss for the associated insurance. It's not possible, even though sometimes to go into harvest because the loss is too high. So, the final conclusion, some recommendations. Yield anomalies with the original data set present some difference, up to 4% difference between original and after you correct. So I prefer to correct the model before to use it. Some people here, I saw many papers that they prefer to use the model as is. I know the model has problem here, but I know the mistakes of the model, but I trust in the final projections. I don't agree with that. Sometimes even though in some discussion, in some thesis discussion, I have some discussion about some professors that use that math. For instance, I'm not showing here, but for the northeast region of Brazil, there is some models that precipitation, like in the Amazon, in the middle of Caatinga. It's totally crazy. So you cannot run the model over there because you're going to get possible to growing crops in the middle of Caatinga. It's not true, okay? So I prefer to correct the model. All the simulation, the good results that all simulation with bias correction present a very similar average yields anomaly. So that means even though if you just use a bias correction or contour correction, you have a more or less similar result for the average projections. The delta math, that it's one of the most used maths for that kind of applications. It underestimated the climate impact, and I have a more deviation between the models and the bias correction. So the idea is that trying to show you the importance of using the bias correction to take off the systematic errors of the models. So this is more or less the idea. Thank you.
Thank you, Santiago. Any questions? No?
Okay, thank you.
Just it was not fully clear for me. What did you find this change in variability with the delta method? Because the variability is the observed one.
Yes, but remember that it's not a linear application. So sometimes, even though you keep the variability of the climate in the present, if you shift for the future, we go to some trade-offs for the crops.
Okay.
So for instance, if temperature is 32, there is don't cause sterilities for the crops, and go to 35, with the same frequency, and go to 32, with 35 you have sterility, you have loss.
Okay.
So it's a non-linear application. That's
Yeah.
why we have, even though affects the internal variability.
As well. Okay. Thank you.
Okay.
Yeah. Good example.
Thank you.
Just curious, what the bias correction methods have you used?
Here I show you, just remove I take the average for each month. So the average precipitation for January, and I take the model. Then I take, for instance, if the model is 2 degrees higher, I take off the model minus 2 degrees for all simulations. This is for more simple with the bias correction just. And other ways, just correct the distribution. So we make a relationship between the distribution for the model and for the observations. So whenever, sometimes they are closer, sometimes they are disclosed. So for that part, you dislocate more the model, and sometimes they are closing from part of the distribution. Basically, you don't correct.
Okay, thank you.
Is there any impact of the changing of time scale for the bias correction?
Sorry?
Is there any impact of time scale? For example, you applied bias correction at monthly data, right?
Yes, with monthly.
Is there any impact? Did you check if you applied the correction for daily basis or?
No,
season?
actually, we take the correction relationships for each month, but we corrected the daily values. Okay. For instance, if one daily event of precipitation in the model is 35, and the observation says that the precipitation is 20 for that frequency. Whenever the precipitation in the model is 20, I input 35. Actually, the correction is the daily values, but I take a factor that it's for each month. Because if you use it for daily, every day of the year, you don't have enough observation to make a distribution. Remember that to have, for instance, if you use 1 month, 30 years, you're going to have 900, right? 900 events, right? If you just use it for every day, you're going to have just 30 events. You cannot make a distribution. So you have to take a higher, or even though if you, for instance, for one specific season or for a specific month. If, for instance, precipitation, sometimes you take very few events. So if precipitation is worse, because some months you don't have any events. So it's difficult to do the correct. You have to do some tricks to deal with this case of precipitation. You have to be careful. Because, for instance, in some months you don't have any events in the observation. For instance, you have events in the model. I forgot to give you a tip. A tip não, qual eu sei? A dica. Não é a dica, é tip. You have to actually I take the same number of precipitation events in the model and in the observations. Okay. For instance, if the model rains 100 events and the observation says for that month is 85, I take the 15 lower events and say that's 0. I take a trade-off that will be 0. So in the way that the quantity of precipitation is the same. The quantity of the events is the same in the model, is the same in the observations. Because sometimes the model rains a lot. So it's have much more events. So if you take the distribution will be affected by the number of the events. So then I say, okay, In the model, if you run, if it rains 0.5 millimeters, it's not an event. Just take off. It's not a rain event. Then I match both distribution. For precipitation. For the rest, it's very easy. It's very different. For temperature, you don't have any risk. But precipitation, you have to be careful.
Other question? No? So thank you, Santiago.
Oh, thank you.
Okay, so next speaker will be Moira Doyle from Argentina. The title. So the title is Using Vic Model to Estimate Stream Flow from Downscale Data.
¿Cómo? So good morning to everybody. I'm Moira Doyle from the University of Buenos Aires, and this talk I'm going to tell you something about how to use Vic model to estimate stream flow data from downscale data. You've been listening to different talks here, and you've heard about a flagship pilot we have here in South America, where we are working with different dynamic models, and we are working with different statistical downscaling methods. And the idea is to use this information, which will evaluate extreme events in southern South America, and see how these extreme events, when they're modeled by different ways, impact on the stream flow in a particular basin. We are going to work in this project is the Uruguay Basin. So Gonzalo Diaz, that works with me and is part of this project, he is running the Vic model for the Uruguay Basin in the National Weather Service in Argentina. So he will be working with the model with this project. We still don't have any results because we're just starting. So I'm not going to talk about the results from the project because we don't have results. So I'll talk about the model, and if anybody of you would like to work with stream flow data, you could use this model. So when you work with regional models or weather forecasting models or global climate models, you will have the water cycle inside the models, and you will have much information about the different aspects of the water cycle. So you can study precipitation, you can study intensity of precipitation, frequency of precipitation, spatial distribution of precipitation, flooding events, drought events. You can study different things. But there are some things that you need a more specific model to study. And in particular, one of those things is the surface and subsurface runoff. So in these global models, you will have vertical levels where the model will evaluate the different variables you need to calculate. And you will have a horizontal resolution. And the models, in general, are trying every time to have smaller horizontal resolutions. We have heard about working with 4-kilometer horizontal resolution to work with convection permitting mechanisms, or I lost the word. And but even if you don't have a 4-kilometer resolution, you will have a good result about what's going on with the weather or what's going on with the climate. In the hydrological models, we don't work with many vertical levels. We don't work with vertical levels in the atmosphere. We have vertical levels in the soil. But the horizontal resolution is very important. So this is an example of the Ashley Bush Subbasin in Utah. It's a work by Obeidillah. And this is the river basin. And you can see you have two rivers here and one here. And you have 3 gorge stations, one on this river and 2 on this other river. And in this case, you have a grid of 4 kilometers superimposed on this basin. And in this case, you have a 12-kilometer grid on this basin. These shaded grids are the amount of stream flow greater than 20 in these cases and greater than 2 in these cases. So if you look at this model of 12 kilometers, you can see that, for example, the output of this grid is not distinguishing this river from this river. So at this point, the output would be from just one river. While in this case, you have very identified the rivers one from the other, and you have grid points that are shaded separately on both rivers. And you can distinguish the output from one river and from the other river. So you can see the horizontal distribution or resolution you're going to work with is very important. So this you wouldn't see in a general circulation model or in a weather forecasting model. You have to go to another kind of model, and this is the hydrological model. So there are many hydrological models you can use. There's one that's very famous, it's called SWOT, and many countries have their own hydrological models. And nowadays, RegCM 4 has a coupled hydrological model. WRF has a coupled hydrological model, but those are a bit more running demanding. If you have to run the model and the hydrological model, it's more time consuming. So you have more simple models like this one that is called VIC, because it means variable infiltration capacity. This model was developed in the United States. But originally, this was a one-layer soil model that was part of 2 general circulation models, the GFDL and the MPI from Max Planck Institute. And this single-layer model had 3 parameters. An infiltration parameter, that means how much of that rain that falls in a grid will enter the soil, how much will run off. An evaporation parameter, that is the amount of soil you have, water you have in the soil, how much will be lost. And then a base flow recession coefficient that regulates the interaction between underground water and surface water. So this was a very simple model. And the next step was to pass to a 2-layer VIC model. That means you would have 2 layers within the soil. And on the top of each layer, you have the vegetation distribution. And for each grid, you can subdivide into different cells and put different kinds of vegetation. And you would have then the infiltration parameter and the evaporation and the drainage coefficient calculated for each grid cell within the grid point. Now, this model had a problem. It underestimated evaporation. And the main problem with this was because there was no mechanism that would bring soil from the lower layer to the upper layer. So to correct this deficit, a new version of the VIC model was created, and a 3-layer model. This 3-layer model now has a diffusion moisture coefficient that allows soil moisture to move between one soil layer and the other. It has now a small 10 centimeter layer near the surface. It also still has the cells within a grid where you can divide the different types of vegetation or bare soil. So this is the structure of the actual VIC you can now define more layers if you want, but with 3 layers, it works okay. So, as I was saying, the land surface is modeled as a large grid, but within the grid, you can have different options. You can have different elevations. You can have different vegetation. You can have water. You can have subdivisions. The model will model the fluxes and the energy balances and water balances. It generally works at a daily scale, but you can work with a subdaily scale. And the water, the excess of water from each grid scale will not go to the neighboring grid scale. It will go to a channel, and that will be part of the stream flow. So this has 2 things. One is that each grid cell is modeled separately. There's no interaction between one grid cell and the next. And to obtain the stream flow, after you run the Vic model, you have to run a routing model that will get all the excess from each grid point and convert this into a stream flow and how it and model how the flow runs within the basin. So this is a small sketch graphic where all of these mean characteristics of the Vic model are summarized. So here, this is the top layer where you have the different energy and water balance mechanisms. And this grid cell, you can divide it in between 1 and n cells, where each cell can have a different type of vegetation, and the n+1 would be bare soil. For each of these vegetation types, you need information like the leaf area index coefficient, the stomatal resistance, well, the kind of vegetation you have, if you have a forest, if you have grass, or you have crops, and the root, the depth of the roots within the soil. So this, you have an amount of information necessary to model the vegetation types. For each vegetation type, you will calculate the evapotranspiration. In general, it uses the Penman-Monteith evapotranspiration equation, where not only it calculates the integrated value of the transpiration from the plants and the evaporation from the bare soil. And then for the 2 upper layers in the soil, you have a curve which will regulate how the water within the soil will be infiltrating. This is the variable infiltration curve, and it depends on the Brooks-Corey equation. The lower layer, the last layer, is regulated by the base flow, and how this the moisture and the flow within this level is governed is given through this the Arno equation that has this type. So in general, the moisture within the soil will move from the surface to the first layers, and only will move to the lower layer when there is an excess of soil in the upper levels. So the variation within this layer will be on a seasonal time scale, on a much slower time scale, while in this other levels it will be more dynamic. So you can run the model on 2 ways, on a water balance form or on a water plus energy balance mode. In the water balance mode, you will, it assumes that the temperature of the soil surface is the same as the temperature of the air above. This mode is much less computational, with less requirements. So you will have, it will run much faster, and you will have less computation problems. The only case when it will need to run the energy balance even though you're running in the water balance, isn't the case when you're working in areas where there is snow or frozen soil. Here it needs to calculate energy balance, so it will activate the other mode. The other mode, it also calculates the water balance, but also calculates the energy balance. And this time, it also minimizes the surface area in the energy balance. And to calculate the temperature at surface, it calculates as an energy balance between the incoming short-wave radiation and the long-wave outgoing radiation. This mode is computationally much more expensive, and it's generally necessary if you want to study problems where the land interaction with the atmosphere is required. So we said that at each grid cell, and at each time, you will obtain the amount of water that will leave the grid point at the surface and at the base levels. So once you finish running the model, you will have a time series for the base flow and a time series for the surface runoff. And this will enter our routing model, which will decide how the moisture or the water from each grid cell will move along the basin and reach the exit point of the basin. So for each grid cell, you can have, there's an option of 8 out points. So in this cell, the water is crossing to the lower grid, and this one is crossing diagonally towards the west, and this one is crossing diagonally towards the east. So you would have, through the 4 sides of the rectangle or square, the outputs, or through the 4 vertices. And the routing model will depends on the slope the terrain has. So this you can obtain from a digital elevation model, how the slope of the terrain is, and decide how the water will move and reach the output. And at the output, you will have the flow for the whole basin. You can also have intermediate output points. They're called closing points, where you can have the runoff for different stations. So another component of this model is the snow model. In this case, your grid point, instead of having different, you can have different vegetations too, but you can have different elevations. Your topography can vary. And so the model will calculate for each grid point the temperature for this grid point at the different elevation bands. It will be scaled to, according to the elevation you have within the grid, it will be scaled to different temperatures. You can also have precipitations for the different elevation bands, and you will have snow cover for the different elevation bands. Within the model, it also calculates the blowing snow. If you have different types of vegetation, you can have the snow that's over the canopy, the snow that's on the ground, and the snow over a lake of ice, or also it works with frozen soil. Another option within the model is to work to model a dynamic lake or a wetland model. This is in this case the grid point. Sorry, this one. In this case, the grid cell will have different types of vegetations, and one part of the grid will be destined to water. This kind of lake has some limitations, because as each grid within the model is modeled individually, there is no interaction between other grid points. The lake is restrained to one grid point. So the lake has to be within this grid cell. And what they call a wetland is really not exactly a wetland, but it's it's the area of vegetation that's surrounding the water. So if this could be a vertical profile of this grid point, and you have the lake covering all the grid, and all the soil moisture is saturated. So there's a balance, there's a movement of the water within the lake, there is runoff, and the level of the lake starts to diminish, and also the water within the soil starts to diminish. So this part here, where vegetation starts to appear because the level of the water has become smaller, is what they call the wetland. Then, given the runoff over the soil, this will bring new water into the lake, and the level will rise. And once the level is will increase its level, the recharge from the lake will increase the soil moisture over the areas where it had decreased. So this is a bit how the dynamics of the lake and wetland model is. Now this has some limitations because there's only one kind of vegetation you can model, and it's shrubs, and not necessarily a wetland. If you want to model a wetland, the vegetation is shrubs. So there's only input from water within the cell, and there are other characteristics of wetlands that are not modeled within this model. So if you want to run this model, what you need, what we've been talking about, are land surface characteristics. In general, for the soil data, the developers of the model have worked with FAO data, where you have the different properties of soil, and then they have also created a vegetation data set for the 14 different types of vegetation at a 1 kilometer resolution. And you will also need topography. These are for the land surface characteristics. And then you will need the input data that mainly the variables you need are precipitation, temperature, wind, vapor pressure, incoming low wave and short wave radiation, and air pressure. The model can run with less variables of the meteorological forcings. You need at least precipitation and maximum and minimum temperature to run the model. So if you have weather stations where you don't have measures from all these variables, you still can run the model. So when you want to run the model, the first thing you have to do is calibrate the model. You have the soil structure of the basin where you want to run the model, and the vegetation of that area, and you have to adjust the parameters of the model for those characteristics. There are 6 main, the model has many parameters, there are about 20 parameters, but there are 6 parameters that need to be adjusted. One is the infiltration parameter. Then you have to adjust the layers of the second and third soil layers, the thickness of the layers. And then you have 3 parameters that are associated to how the base flow will be in the area. These 3 parameters need small adjustments. They're not very difficult to adjust. The infiltration parameter and the third layer are the parameters that need more work. And you have to calibrate them by trial and error and independently. So once you have your model calibrated for using a set of data, then you will validate the model using an independent set of data and see how well you represent the stream flow. So to see that, you need a stream flow at an output point of the basin where you want to run the model. In general, to calibrate and validate the model, you will use observations from gauge stations or weather stations. And these observations will have to be gridded onto the mesh where, with the grid size you want to run the model. The VIC model has been run with 1/8 of a degree, 12 kilometers, 6 kilometers, or 4 kilometers, and has had good results with all these grid sizes. Then you can also run the model with using general circulation models or weather forecasting models, and that output you have to downscale to the grid where you want to run your model. And as you've been hearing throughout the talks here, when you work with models, particularly with with the climate change scenario models, the bias correction step is also very important, because the hydrological model is very sensitive to precipitation. And if the precipitation is not well modeled, your output from the river flow will not be very good. So these are a couple of examples of people that have worked with the big model using global models and how they have proceeded to convert the global model to data available for the big model. This is a work by NAS and all in 2018. They worked with all the river basins in the United States. So you can see you can use VIC for a very small watershed, or you can use VIC on a global, on a more regional scale. And what they try to see is how the impact on stream flows of the changes in climate. They worked with 10 CMIP5 GCMs. They were all dynamically downscaled using RegCM 4. They passed from the resolution of each model to an 18-kilometer resolution. And they modeled historical and future scenarios. But before entering the VIC model, they had a second step. The 18 kilometers were spatially interpolated onto a smaller grid of 4 kilometers. And then the data were bias corrected using a quantile-based method, similar to those that Santiago was explaining before. So, and all this data was entered into the VIC model to see what happened with stream flow. I won't go into detail with all the papers. You can look at them then if you want. I just want to show you some examples of the way people proceed to pass from a global model to a hydrological model. This other paper, it's they modeled in a basin called Athabasca in Canada. So what they wanted to see was the change in the snow water equivalent. They also worked with 24 models using future scenarios for two greenhouse different emissions. So these 24 climate projections came from 6 CMIP5 GCMs, and considering 2 climate scenarios and 2 different time periods, that gives a total of 24 climate projections. Now, for this paper, they used 2 bias correcting methods. One is the bias correction spatial downscaling, and there is the bias correction climate imprint. Why did they use this? Because there's a paper by Murdoch who used different downscaling methods or bias correcting methods, and this paper concluded that these are the 2 best methods he found. And so an institute in Canada decided to downscale the models using these 2 methods. So they took the input that was already prepared and run the VIC model to calculate how what would be the change in the snow water equivalent and for the different scenarios. So this is the basin, but they divided the basin in 3 parts. They had the lower basin, the middle basin, and the upper basin, where the upper basin is within the higher parts of the mountains. So this is an example of using the snow model of the VIC and using the different elevation bands within the grid cell. And here you can see some of the results they found. There are small changes. There are very small changes for the near future and the far future for the RCP 4.5, but there are quite big changes in the snow melt maximum for a very extreme scenario and a future event. And what they also found is that the day when the maximum snow water equivalent starts is becoming earlier within these scenarios. And another example, now here in South America, this is in central Chile. They modeled 4 different river basins, Itata, Maule, Mataquito, and Rapel. And they used 2 statistical downscaling methods to download 1975 GCMs. They used one for daily precipitation, which was regridded onto a 0.25 grid, and they used a statistical bias correction technique. In this case of precipitation, as Santiago was saying, there is problems with daily precipitation, so they used the seasonal precipitation to downscale or to bias correct the precipitation. But for the temperature, they used the monthly values. So you see, to get to run the big model using input from other models, you have to pass by different steps. So you have the global model. If you have, you're using climate scenarios, you have the climate scenarios that are included in the models. Then you have the regional climate models, if you are using a regional climate model to download the model. Then you have the bias correction method, and you have the, if you want, you also use a statistical method. Each of these steps has some uncertainty. And also running the VIC model or the hydrological model has another uncertainty. This is something important to take into account when one discusses the results, because one can say you have one given result, but if the model has a very large uncertainty, then the result is not very certain. So this paper worked to evaluate the uncertainty, in particular of these 3 steps: the regional climate simulation, the statistical post-processing, and the hydrological modeling. There are other papers that have evaluated the uncertainty, and most of them, according to this paper, concluded that the global climate simulations are the step with the highest uncertainty. So they used downscaled GCMs through the CORDEX East Asia project. They had 4 regional climate model outputs. They used 5 outputs. They used 5 different statistical post-processing, and they used 2 hydrological models. They used VIC and they used SWAT. But to run the uncertainty analysis, they selected 2 regional climate models, 2 post-processing processes, and the 2 hydrological models. And what they find is that they analyzed there are different methods to analyze the uncertainty. The method they chose is the variance analysis. And they analyzed 2 variables: the day of maximum dam inflow and the 30 days minimum dam inflow. So an excess of stream flow and deficit of stream flow. And they found different results for each variable. For the maximum stream flow, they found that the highest uncertainty is given by the regional climate model, though the hydrological model still has a high uncertainty. For the days with minimum inflow, the highest uncertainty is given by the hydrological model. And this is because the causes of these uncertainties are given by different aspects. In the first case, the high flow is directly affected by precipitation amount. So if you have a high uncertainty in the precipitation in the regional climate model, you will have probably a high uncertainty in the stream flow. And on the other hand, the 30 days minimum flow is more dependent on the soil moisture condition, and that's given by the hydrological model more than by the regional model. So I'm finishing. This is an example of work done by Camilloni and Saural and Montrul on the La Plata Basin. This was part of the La Plata Basin project, Claris, yes, Claris project. So they, in this project, there were different, these are for the previous scenarios, for the CEMIP 3 scenarios. There were 5 regional climate models who downscaled, dynamically downscaled these scenarios for 2 periods, the near future and the far future. And what they wanted to see is how the flooded areas on the coast areas of the main rivers of the La Plata Basin would be affected by changes in temperature and precipitation. So the variables they used to run the Vic model were daily mean temperature and maximum temperature, precipitation, with all the variables, and particularly they were interested in incorporating the relative humidity, because if you don't incorporate all the variables, which when they're coming from a model, they are consistent among them, the model has to calculate the remaining variables. And sometimes these calculations can be a source of error. So if you have all the information available, it's better to include all the information. So these regional downscaled models were bias corrected for precipitation and temperature using the quantile-based mapping. And what they found is that the future temperature rise and precipitation would give an increase in the river flow in the basin, but the different models they analyzed had very wide uncertainty among the models. So there's such a great variety that it's difficult to have a correct answer for this question. And the last example is the Ibera wetland. So in this case, what was used is the lake wetland mode of the model. This was also part of the Claris project, and it's also part of the same group, and the leading author is Natalia Montrul. In this case, they only used 4 regional climate models for the same time periods. And the Ibera wetlands is one of the, this is here in Argentina, it's this small place here, this is the Ibera wetlands, and it's worldwide known on account of the biodiversity there is within this wetland, and because there's a lot of water too. So in this case, the Vic model is run for 1 grid cell, just 1 grid cell. So all the area of the Ibera wetland is averaged onto the grid cell. And the different, so you will have the water and the different aspects of the topography and of the vegetation on the different cells of the grid cell. So the meteorological and the land cover and soil data are spatially averaged. The method they use for the data is the same as the other, because it's part of the same project. So it's the same data they use, but for a different different basin. And what they find is that in a future, the temperature and the precipitation will rise, and the level of the wetland will also rise in about 10 centimeters. But this result is also within the limits of the uncertainty. There's a very high uncertainty among the results of the different models they run. So this is the web pages where you can access the Vic model if you're interested in running the Vic model, and you have information on the Vic model, and that's all. Thank you very much.
Thank you, Moira. Any question? No?
Hello, Moira.
Hello.
Thank you for your lecture. You said a lot about uncertainties and all this effort to translate these climate simulations to hydrological simulations. And what is, I don't know, you may not know the answer exactly,
Probably.
but what do you know how we would deal with it? with these uncertainties and work with it. And
well, if you find uncertainties in the model, then there are things in the model that have to be adjusted. Say you have the global climate scenarios. They are not a perfect answer, so they have uncertainties because the emission scenarios are not exact, and so probably we'll never have an exact emission scenario. But you still can. There's a lot of work to be done with the global and the regional climate models to adjust the observations. And if you reduce this uncertainty, there are things that probably you will never reduce. But if you can reduce this, then you will reduce the error you're inserting in the next steps of your process.
Another question? No? So thank you, Moira.
Rosemary.
For example, for hydrological model, the soil moisture is too important.
Yes, very.
Yes. For example, for some case studies, I don't know how long is the simulation to capture, for example, one excessive stream flow.
In general, some papers say that you should run the model 1 year to have a stable run.
Another question? No? So thank you, Moira. And now coffee break time. So how many? How long? 20 minutes. And then 20? Yeah. 11:05. See you here again.
Valendo, viu?
E quando vai ser a defesa?
Do quê? Não, ainda tô terminando lá. Eu assumi a modelagem, aí eu tô pondo em ordem a casa lá, né?
Você tá onde? Lá em
São José dos Campos.
São José dos Campos.
Aí, como tem laboratório lá, tudo pesquisa, né? Todo dia. Só que com outro ritmo. Iniciativa privada é meio... eu fiz algumas coisas que eu fiz agora, fiz duas pesquisas que se eu tivesse feito doutorado já teria conseguido defender o negócio, sabe? Deveria ter estudado. Eu nunca trabalhei tanto, eu estudei tanto quanto na prática.
Mas é assim mesmo.
É assim, bom, né? Eu gosto disso. Adoro. É todo mundo que eu gosto, que é modelagem. Eu duro é lidar com as pessoas, só isso. Com modelagem as pessoas têm ódio, né?
Como assim?
O cliente quando erra, essas coisas, é uma cascata, sabe? Eu recebo e-mails horrorosos de pessoas internas, né? Que eles são pressionados e tal. As pessoas têm expectativa, né? De acerto, né?
Mandei pra... Eu só tenho Dandora. Jura? Se você quiser, eu tenho... Sei. Ela que está organizando? Tem o Geraldo aqui.
Aqui.
Vai a giocare, ho detto, ma io dopo mi arrabbio e poi Naim arriva il giorno dopo e proprio
são com RegCM, 25 quilômetros, usando esta versão. Aqui tem boa precipitação, mas não há precipitação aqui quase.
As minhas estão até 8, 7, 8 milímetros.
Sim, são mais secas, mais ou menos assim, mais ou menos assim.
Sim. E tem todo.
Sim.
Eu tenho aqui a...
Sim, amanhã nós vemos.
Ok, amanhã nós
sim,
vemos.
Porque
Perfeito, obrigada.
hoje
Sim, hoje
eu tive classes de las 8 às 9:30.
Ok, sim.
Tenho que arreglar coisas com os estudantes. Amanhã vemos. Quando volto? Sábado?
Sábado, sim, eu posso.
Também?
Sim.
Não. Amanhã estão todos aqui durante...
Sim.
Ok. E mira, é muito complicado, por exemplo, esta versão acho que foi 50, esta é 50 quilômetros, não é 25.
Ah, 50?
Esta sim. Mira, esta é 50. A versão 4.3 é que a Marta usou em seu teste de doutorado. Havia mais lluvia aqui, sim?
Sim.
Um pouco mais, não? Um pouco mais cerca disto. Aí depois, esta é uma mais moderna, 4.5, e depois vem a 4.7. Melhorou muito aqui, mas, por exemplo, aqui, na minha opinião, está pior.
Entende? Algo assim. Sim, para mim também é uma coisa assim, mas com menos chuva.
Sim. Nós comparamos, porque vamos na minha sala, que eu tenho umas figuras similares a essas, mas com as corridas que te enviei.
Sim.
Aí, você, por exemplo, para as moções, provavelmente você pode fazer uma redefinição do como está buscando.
Sim, o que eu achei é que a circulação está muito boa. Tem muito boa variabilidade monzônica, também, mas o que passa é que não há convergência, não há ascenso e não chove. Isso é geralmente o que eu estou olhando.
E isso muda. O mais importante para você é ver como está cambiando em função da resolução.
É melhor, sim. É melhor a 25 que
sim,
a...
Mira, isto é na Amazônia. Esta versão, que é de 25, está mais seca.
Claro.
Assim, do que as outras.
Claro, mas acho que pode ser a configuração da convecção.
Sim, e eu penso que a que está usando está um pouco mais seca ainda que esta. Sim? Está muito seca aqui e... a que está usando ainda na apresentação em ICTP, da Michelle Reboita, que tem umas figuras com uma versão que você está usando de 25 km. Você pode comparar. Por exemplo, em La Plata, Basin, não é tão malo, entende?
E você também mostrou umas figuras de alguém que analisava diferentes resoluções com o RegCM para um mês. É você?
Eu fiz.
Você tem uma publicação? Porque eu não...
Eu tenho... não tenho.
Eu não conhecia e para... ok, só para citar, então ainda
você
não
pode
está
citar,
publicado.
não está publicado, mas está na página do ICTP. Você pode citar com uma apresentação de congresso.
Ok.
Na verdade, eu até gostaria de terminar isso, mas não tive tempo. Sim, porque desde que maio, depois fui para a Bolívia e depois tudo que hago desde há muito que estamos organizando esse workshop. É um processo muito lento porque tem que pedir dinheiro. Mas acho que há outros, por exemplo, há um paper muito talvez isto um paper de acho que Eutair.
Sí, uno que es ahora de 2018, que aumentou o domínio.
Eu não creio muito naquilo porque trabalho muito tempo com isso, mas eles discutem a questão do tamanho do domínio e acho que mas todas são a mesma resolução, não?
Eu tenho um montão de trabalhos do RegCM, sim, da Revoita também, eu conheço todos.
Então, ele discute que se você põe dentro...
Ok, sim,
não sei
muito. Eu já vi.
O meu você pode encontrar aqui. Assim de eu encontro. É mesmo. Essa configuração de RegCM, embora lá no promédio da chuva não esteja bem, essa última, é a primeira vez que eu vi o RegCM a ser bem a variabilidade interanual. Lo que mostrou Michel. Se você, por exemplo, a seca de 2015, nós fizemos 7 simulações em clares e não conseguimos mirar a seca, nenhum no modelo ha hecho. E é a primeira vez que eu vejo isso em RegCM.
Eu também grafiquei, eu calculei um índice monsônico, o Lisan, que tem várias variáveis de circulação e também dá muito bem comparado ao interino.
Sim, é o que temos. Sim. E aí, Rita? Então, aqui, por exemplo, ela... lá também é a minha apresentação, se querem ser uma referência. Ok? Sim.
E as apresentações daqui vão...
A gente vai, depois vamos organizar. Assim. Por exemplo, aqui, a simulação que você está usando, essa aqui, eu acho, essa aqui é uma... Não, essa. A vermelha, eu acho, a vermelha ou a verde, uma das duas. É a primeira vez que eu vejo, por exemplo, o RegCM dá um perfil tão perfeito na Plata Base. Isso é na Plata. Na Amazônia é mais seco. E ela faz uma comparação. Então, aqui, uma dessas duas simulações é a que você está usando. Então, você pode comparar com a que está lá também. Ok? Sim. Mas amanhã eu vejo um pouquinho também. Talvez não muito. Cadê o seu? Porque eu mexi tudo. Depois a gente pode deixar na página, porque todo mundo quer as apresentações, mas é bom mesmo, você viu? O ICTP deixa lá, aí quando eu preciso ver alguma coisa, eu vou lá direto, não preciso ficar olhando no meu computador, que é mais difícil. Vou deixar uma aguinha para você, ó.
Obrigada, Rose.
Se você
Tô nervosa.
Já estamos atrasados.
Mas o meu é rápido, Rose. Não fala muito. O que eu falar?
Não, mas é legal. Sabe o que é? Aqui é um workshop de clima e tal. Mas, por exemplo, o pessoal falou dessa coisa de resolver modo, entendeu? E também das aplicações que você pode fazer com o modelagem. Por exemplo, você já falou de agricultura, a Moira falou de hidrologia. Acho que o Marcelo vai falar de interação oceano-atmosfera, entendeu? Mas sempre a ideia é o modelo.
Tá ligado, será? Tá, né? Tá ligado, né?
Botar um pouco.
Não, não precisa, tranquilo.
Let's start again. Ready? Okay, so next talk, the title is Modeling Air Quality in São Paulo with RegCM, will given by Rita Inoue. She's a professor here in the Department of Atmospheric Science. So.
Thank you, Marta. Well, good morning, everybody. Thank you for inviting me for this talk, for this workshop. I feel a little bit as an outsider here because I'm not going to talk about climate, but about weather. And not only weather, but air pollutants and not greenhouse gases. And my talk is going to focus mainly on emission processing and modeling. So, I'm part of a group, LAPAT, which is Laboratório de Análise de Processos Atmosféricos. You may know Fátima, Fábio, and Adalgisa. We have an interest in characterizing the aerosols and the atmospheric composition here in São Paulo. We have a lot of experiments. We have tunnel experiments. We have a lot of instruments, and we use all of this to model air pollutants here in our city. So, atmospheric emissions, transformation, and deposition of trace gases. I usually start with the sources of these air pollutants. So here would come the emissions. The sources may be anthropogenic or natural sources. And then this material is thrown to the air, into the atmosphere, where they may disperse or may be transported. And also they may have many chemical reactions and transform into other elements. And once they are in the atmosphere, they may also suffer indirect or direct deposition. So they may be run off by rain or may have dry deposition. And so I'm going to focus basically here on the anthropogenic emissions. And the WRFCAM, which stands for the Weather Research Forecasting Model with chemistry, makes this part here, and the output is given then in our operational modeling, which is run every day for some days. So, good emissions estimates are the start of any environmental assessment. I heard Moira talking before me, and she said that even now the emission scenarios are not very good. They are not very precise. And we suffer the same thing here when dealing with air pollutants. So, emissions, they may be either natural or anthropogenic sources. The natural sources may come from volcanoes, natural fires, dust storms, The sea and forest and even lightnings. They contribute, all of them contribute to air pollutants, emissions. And for the anthropogenic sources, we have plants. Here in São Paulo, I'm not sure if you have been a victim of our transportation system, but we suffer a lot with all the vehicles that are here. In our countryside, there are also people who use fossil fuels to use inside their residence, and we also have a lot of industries. We also have non-road transports and mining activities. So I'm going to talk basically about vehicle emissions because this is the main source here in São Paulo. So when you see a vehicle, we have a lot of emissions from different processes. I think that the main process that we are aware of is from the exhaust emissions, and the main pollutants are CO2, CO, hydrocarbons, NOx, and particulate material. But we also have other sources inside the vehicle which must be accounted for. For example, the evaporative emissions. When you fuel your car, some of the fuel escapes to the environment, and these emissions should also be accounted for. When you brake your car, you're also emitting because of the tires. Also, when you're running your car through a road, you have to consider there is suspension of road dust, and this would be the main parts of the emissions from the vehicles. So the main pollutants here would be hydrocarbons, volatile organic compounds, particulate matter, carbon monoxide, carbon dioxide, and nitrogen oxides. And here we also have sulfur dioxide as an emission from vehicles. Power plants emissions, they are basically from nitrogen and sulfur dioxides. We have some power plants here, but here in Brazil, we are most all dependent on hydraulic energy. So we are not suffering so much with this kind of emissions. We also have biomass burning, so I think everybody sees the Amazon being burned, and so we have a lot of biomass burning, and these emissions would be, the pollutants would be CO, NO, methane, a lot of VOCs, and aldehydes and VOCs and hydrocarbons. We also have, not only in the Amazon forest, but here in São Paulo, we have people who burn their waste. So this is also a concern here in our state. So how do we calculate the emissions? We usually have an emission factor for the activity that we're dealing with. And the emission factors is the mass of pollutant produced per unit of activity. And they vary by pollutant, equipment, and source. They are found in models, national tables, and source tests. And for example, how much CO does a light-duty vehicle emit in one day? The emission factor taken from mobile, which is an emission model, would be 2 grams of CO for each kilometer that the car runs. So if the car runs about 30 kilometers a day, the emission of this car would be 60 grams of CO per day. This emission factor is an average. So if you accelerate your car, you emit something. If the speed of the car is high, the emission usually is higher. If the car is climbing, it's different. So this is an average for CO emission. And the same for all the other air pollutants. Here in Brazil, we have the IBAMA, which would be our Federal Environmental Protection Agency, our EPA. And locally, here in the state of São Paulo, we have CETESB, which is our local EPA. And these agencies, they have some emission factors for vehicles which are used in our models. This comes from CETESB, and so here we can see that the automobiles, we have more than 9 million vehicles as automobiles, or light commercial vehicles, heavy commercial vehicles, buses, and motorcycles. And here we can see that we have a large fraction of the automobiles, not only in São Paulo, but in Brazil. So the light vehicles are usually fueled with gasoline or ethanol or a mixture of both. And the high-duty vehicles are fueled with diesel. And motorcycles also are fueled with either gasoline or ethanol. And here we have the flex motor, which can run in whichever mixture of alcohol or gasoline the user wants to have. And here is the emission inventory from CETESB. So here we have the amount of, for example, CO emitted by all the automobiles here in São Paulo state, here in São Paulo metropolitan area. And we can see that the light-duty vehicles contribute most with CO and hydrocarbons, and the heavy-duty vehicles with NOx, particulate material, and SOx. And also here we have the industries, which also contributes a lot with NOx, particulate material, and SOx. And this would be the contribution for each pollutant from each source. So here you can see also that CO and hydrocarbons are mostly emitted by light vehicles, whereas NOx, PM, and SOx are mainly emitted by heavy-duty vehicles and industries. It's important to note here that the particulate material we categorize in coarse material and fine material, coarse aerosol and fine aerosol. The coarse aerosol is mainly emitted by the sources, so they are primary pollutants. However, the fine aerosol, which has diameter less than 2.5 micrometers, they have a huge source, which is photochemical chemistry. And here would be this process. So 50% of the fine aerosol is not directly emitted, but they are formed in the atmosphere. So how do we process the emissions? So air quality models usually needs good quality emissions input, which should describe all the anthropogenic sources, be consistent in time and space, and provide the best estimate for the emission. This would be our dream. And we have two kinds of methodologies to do this modeling. So we have a top-down approach, which would be consider the global and national or local inventories with low resolution, use some proxy data to get the high resolution emissions. The other approach would be the bottom-up, where we have each car, what it is emitting, how much, what is the speed of the car, how much it travels per day. And so this would be a very time-consuming, but really more proximate to the reality than this one. Usually we use this kind of approach, but here we had a doctoral student that made this kind of model. So some terminology here for the emissions. Inventory is the estimate of pollutant emissions at a given spatial unit, which was an example that I showed you as the CETESB table. The model grid, I think everybody here knows how to model, so I may skip this slide. And I'm going to the emissions processing. So we have among the anthropogenic sources, we also have another classification, which would be area sources, mobile sources, point sources, and biogenic sources. So the area sources are those that are spread through an area. The mobile sources are mainly those that comes from vehicles. Point sources are mainly industries, and biogenic sources are those from forests and crops. This would be a model from an output from the United States, which would be great if we had something like this also in Brazil. Unfortunately, we don't. And well, then the purpose to have this emission processing is convert the emission data into formats that are required by the air model, the air quality model. So, so the primary functions would be import data into the system. We have to allocate these emissions throughout the space that we have inside the grid. Unfortunately, we have also to do this chemical allocation because I said that we have emissions of hydrocarbons and VOCs, but inside these hydrocarbons and VOCs are a lot of elements. So we have to classify these hydrocarbons and VOCs into some classes. This would be the chemical allocation or speciation of the emissions. Also, we have to make a temporal allocation. So we know that a car runs around 30 kilometers per day, but we have to know exactly how much it runs from 6 to 7 o'clock, from 7 to 8, and throughout the day. We have to merge all this information, and we have to guarantee that there is some quality in this output. So here is an example where we have information, for example, for the United States, there is information for each county, and then these emissions are processed so that for each hour we have for each pollutant how much is emitted in each grid. Also, some temporal allocations must be made. So usually we have monthly or annual values, and we have to put it for a diurnal with a diurnal profile. There are some available gridded emissions database, such as EDGAR, for some, mainly for greenhouse gases, but also for some air pollutants. And how we use all this information that I gave here inside our metropolitan area. We use it for the WRF-Chem for academic and operational purposes. We use the GFS, the GFS forecast model of 1 per 1 degree for meteorological initial and boundary conditions. Usually it starts at 12 UTC, not 0, for 48 hours. And we use it only for one grid, which has 9 per 9 kilometers of horizontal resolution, and it covers mostly the São Paulo state. The emissions that we use, that we have to input in this WRF model are basically the mobile sources, and so we use information from our local EPA. We have also some emission factors that are given by either our local EPA or which we measured inside and estimated from tunnel experiments. The VOCs speciation are basically come basically from these tunnel experiments. Vehicular activities come from the CETESB, and spatial distribution. I'm going to show you how we started and how we are now. So the vehicular emissions are basically the same process that I gave you that example. So we have the activity of the vehicle, which is length per time, or how much kilometers per day the vehicle does. How much is the emission factor for each pollutant, for each kind of vehicle. So a car emits different amount of CO than a truck, than for a motorcycle. the emission factor, which would be how much and the number of vehicles, the number of each type of vehicle. And so we use this. It may be simple, but it's kind of tricky. So how is our vehicular fleet classified in different types of vehicles? Here in São Paulo, we have basically 40% are light-duty vehicles, which uses only gasoline. Only 3% of our fleet uses alcohol only. They are rather old, these vehicles, and flex fuel vehicles are around 36. So most of our cars are from our light-duty vehicles. We have a small percentage of heavy-duty vehicles. However, this small amount, they emit a lot, especially NOx and material particulate, and also SOx. We have some estimates for how much each vehicle drives per day, from 400, 300 kilometers a day for the light-duty vehicles to 100 or more for trucks and buses. And our motorcycles here, they also run a lot here in São Paulo. And we have here a lot of emission factors for each type of fuel: gasoline, ethanol, flex fuels, trucks, motorcycles using gas or flex fueled. And then we have to split all those hydrocarbons into a number of classes here. And then we come to the model domain. So here is our state, São Paulo state. Here is Rio de Janeiro, Espírito Santo, Minas Gerais, Paraná, and Santa Catarina. So this is our model domain. How do we spatially allocate those emissions here in that grid? So we first started with satellite view of the Earth at night. And so we had this information of how much light that was emitted from our cities. And from this, our grid here would be zoomed here, and we have some kind of spatial allocation of the vehicles inside our grid. So here you can see that São Paulo is mixed with a lot of other cities around the metropolitan area. We have some roads here. This road goes to Rio de Janeiro state, so it's a very important road. Here we have Campinas, which is also a large city. And this was our first trial to spatially allocate the emissions throughout our state. And here it's in a bigger. Another way we tried to do it was with smoke, which is also an emissions model. And it was also with that information from the satellite. So here you see that we can see São Paulo here and all the other cities. And since it's saturated in terms of light they are emitting, the emissions here are all the same. And we know that that's not true. But it's kind of, it was a good advancement for our modeling. So we first started with smoke. We also had a student collaboration to make pixel by pixel with this model here. So the student would put a red dot where we said this is the Marginal Tietê and Marginal Pinheiros. We are around here more or less. And so we said these are streets with a lot of vehicles. And they just put a red dot there. And where, for example, in rural areas, they put no dot there. So it was basically a manual process. But we had a 1 per 1 kilometer of resolution, of horizontal resolution for the emissions. And then finally, what we used was the map link information. So this map link gives you how much of a street you have in your city. So we use it for GPS, for example, to go from one place to another. And we use this kind of information. So we have here for the whole São Paulo state and other states around. And we have for each the location of each street inside the model. And we made a 9x9 grid, horizontal grid. And what we did was that we counted the length of streets inside each grid. So this would be a kind of a density, a total road length per cell. And our hypothesis was that the whole number of vehicles inside this area was proportional to the number, to the density, to the total road length in each cell. Okay? And so we could spatially allocate these the emissions for each grid in our domain. For our temporal resolution, we also had students' collaboration. We filmed inside tunnels and other streets, and the students counted how much vehicle were passing in every 15 minutes for, I think, 1 week. And this is the profile that we get. So the blue profile is for the light-duty vehicles, and the red profile is for the heavy-duty vehicles. And this would be the emissions, varying temporally from 0 to 23 UTC. And it's easy to see where we are, right? We are right here in São Paulo City. And this would be CO emissions, and the others would follow some pattern very similar to this. So now that we have already designed how the emissions are, we use WRF-Chem to make the atmospheric processing. And now we are going to see what are the results. So we have some configuration for the WRF-Chem model, and those we run it daily, and the outputs are here in this website. And I have just picked some. So it started on the 6th of November, and this would be quite now. It's 13 UTC. We are only 2 hours from Greenwich, so it would be 11 o'clock. And here we can see temperature at 2 meters and surface wind. So we have a temperature around a little bit less than 20 degrees. I think it's hotter, but it's okay. Winds are usually higher. The speeds of the winds are usually higher in the model than when observed. But we can see that we have this kind of circulation here in São Paulo. Precipitation, we didn't have much precipitation within this hour, but it's only for 1 hour. So the forecast, I think it's rather good, because I saw there was some precipitation here during the morning. And now the air quality. So this would be the CO concentration here at the surface. So here in São Paulo, we would have something like around 1 ppm. I think it's lower now because we had a lot of wind, and also the air is relatively clean. So I think it's overestimated. But the spatial distribution, I think it's more or less what we would expect. So the higher concentrations are near the bigger cities. So here we have Rio de Janeiro, Vitória, and here Curitiba, which are the capitals of each state. And then for ozone, so now ozone is really low. We have less than 20 ppbs. But usually we don't have, ozone is usually higher during the afternoon, and usually not around our city, because we have a lot of NOx emissions, and NOx also consumes ozone. So in the afternoon, probably we have emitted a lot of air pollutants here, and they go downwind, and the and the higher emissions would be found at the countryside. And also here, I think it's it's less cloudy than here. That's why we also have a lower concentration of ozone. So I'm just going to show you briefly a PhD thesis of a student of mine who has already presented his model. So he would be a very, very, very high resolution of emissions, and he had all his doctorate to make this kind of output. Thank you.
Thank you, Rita. Do you have any questions? No?
Sorry, it's a curiosity question.
Okay.
Because you mentioned the different natural factors that are sources of components, and one of them was lightning. How does lightning create aerosol?
NOx.
NOx?
Yes, it is an important source of NOx for the atmosphere.
Okay, thank you.
Other question?
Thanks. Rita, how is the resolution of this last map?
I think it's 500 meters.
500?
But it can be even higher.
Yes?
Yes.
Okay, thank you.
It's just that our models cannot resolve 500 meters convection or other things.
Okay, but after that, you interpolate for 90 kilometers to use in the Earth.
No, that was another methodology. That was a top-down. This is a bottom-up methodology.
Okay.
Because here, Sergio has done only for the metropolitan area of São Paulo, and we wanted for the whole state of São Paulo, part of Rio de Janeiro, Paraná, and it's really time-consuming. So we didn't do this for the operational models.
Okay.
What is the cost of computational to run RegCM?
For these 9 kilometers, for 48 hours, it runs in 6 hours. But we don't have aerosol.
Hi, I was looking in your precipitation from today and the emission pattern. So moreover, looks like that the emission pattern is forcing the precipitation?
No, there is no interaction between the air pollutants and the meteorological parameters. So although there is emissions of particulate material, they are not activated as CCN. So no. What happens is if you have precipitation, this particulate material is removed from the atmosphere. So the concentrations get lower. But it's not a CCN that is activated, because this would be really time consuming.
So it's a coincidence. You can go to the next slide.
With CO?
Yeah, that's... No?
And you see the precipitation is really low here. It's less than 0.5, sorry. Precipitation here is less than 5, sorry. It's less than 5 millimeters. Yeah. And it's spread through a 9 per 9 kilometer grid. So no, it just removes some of the CO.
Okay, thank you.
Other question? No? So thank you, Rita.
Thank you.
Okay, so next talk will be Regional Climate Dynamics and RC Interaction. Will given by Marcelo Barreiro from Universidade da República. Universidade da República. Yes? No?
I will see.
Okay, so welcome.
Thank you. The pointer is.
The pointer is.
It isn't?
Yes, yes. So this is a laser, forward and backward.
Oh, okay.
Okay.
Thank you. Okay, hello everyone. So I'm glad to be here to give the talk in the context of this second workshop. It has been really, really nice workshop so far, and hopefully it will continue this way. I'm going to talk about regional climate dynamics and Earth interaction. But I'm going to start, before starting with Earth interaction, let me say a few words about something that I'm not sure it has been stressed enough during the workshop. And I want to show this, showing you this picture. This picture is the trend from 2010 to 2060 in precipitation in a global climate model, only one model. These are 40 members, only one model, initialized with different atmospheric conditions. Same scenario, different initial atmospheric conditions only. Okay? As you can see, there are regions that independently of the ensemble member you take, essentially there is an increase in rainfall. So this is essentially a region where the external forcing is playing the largest role, like, for example, like greenhouse gases. But if you look at other regions, for example, Eastern Brazil, you can see that in some ensemble members, there is an increased rainfall over here, while in other members, there is a decreased rainfall over there. Same model, only different initial atmospheric conditions, same ocean conditions, same land conditions. Everything else is the same and same forcing. So here you have a blow-up of just two. This is ensemble number 4, this is ensemble number 9. So as you can see, this region is about the same in the two members, but this region, the region of the South Atlantic Convergence Zone, this is for the DJF, the trends are essentially not opposite, but almost opposite. Same model. So how can this happen? Essentially, what is happening here is that the internal climate variability is much larger on these time scales than the externally forced signal. This is particularly important for near-term future projections. Okay? If you wait long enough, like 2100, you probably will have an external forcing that's going to get beyond the internal atmospheric variability. So to summarize this, I like this slide. This slide by Xie. And what it says that if you want to look at the uncertainty, okay, on changes in regional climate, for example, rainfall patterns in a future, really what is important is the atmospheric circulation. What I mean by atmospheric circulation is the internal variability in mid-latitudes plays a big role in determining the changes in regional climate, and also the atmospheric response to the different patterns of sea surface temperature. And then after that, these things are modulated by the regional land-ocean processes. This is very different than this case. This case is when you want to look at, for example, the change in global mean temperature. The change in global mean temperature is essentially given by the radiative forcing, like aerosols, and climate feedbacks, which is the main responsible for uncertainties are the clouds. So these are essentially thermodynamic processes, and these are essentially dynamical processes. So depending on the kind of problem you want to tackle, you really have to be careful in taking into account the internal atmospheric or climate variability. Okay, so this is what most people have worked in the last 100 years, essentially. And this is something that we are trying to figure out right now. Okay? The take-home message, I like the take-home message from these slides, from a paper by Desert et al. In 2014, essentially says, any single model run or any multimodal average lacks information on the expected range of climate trend outcomes associated with natural variability, limiting utility for decision-making purposes. Okay, you cannot take just one run from different models and do a composite, because you don't know the natural variability that each model independently has. Okay? So by the same token, regional climate models and statistical dynamical downscaling procedures should make use of the range of ensemble climate forecasts conducted with global models. So I think this is very relevant for this workshop, because we really have to, when we are going to use regional climate models, we really need to take into account the internal variability of each individual model in order to do our projections using regional models. Following this, this understanding of the climate change, the climate dynamics group of the World Climate Research Program wrote a perspective in Nature Climate Change in which we essentially outline some challenges and opportunities for improved understanding of regional climate dynamics. And you can read it afterwards. But essentially, the point is, I like this change we wrote, is the challenge is to produce theories of regional climate change on a par with, for example, theories of pyroclinic instabilities that can be rigorously tested. So this is what we lack. Essentially, we don't know what to expect. So we run models, but we don't really have a predictive theory to say, okay, this is what we are supposed to expect from what we are running. Okay, so it's bad for me to tell you, to recommend you to read this paper, but I think it has some interesting points, and in particular, the idea is that if you want to make progress on the regional changes in the near future, we really need to understand what is the response of storm tracks. We have to really understand the interbasin connection between the oceans and so far. So the dynamics has to be taken really into account. Not only the thermodynamics, that is what people mainly focus when they tend to think about climate change, which is the greenhouse gases, aerosols, etc. So we really need to look at the dynamics of the system. So now this was some kind of introduction. I want to look now into a particular problem that I have been working, and it's the South Atlantic Convergence Zone. As I showed you before, this region, if you look at the trends in one particular model, has a large variability in the changes, in the projected changes in climate for the near term at least. So we really need to understand the dynamics of this region in order to have some predictive capability and to know what to expect from for the regional climate change or for the global climate changes that will give us the models under some scenario. So I'm going to talk about this South Atlantic Convergence Zone. And if we look at the processes that dominate the variability of the South Atlantic Convergence Zone, essentially it's affected for many things. It's affected locally by the Amazon convection, obviously, the transients coming into the region. And then if you look at the major modes of variability that control the changes in the SACs, you have El Niño, you have the Madden-Junior oscillations, you have also the tropical Atlantic variability, and there might be some connections to the southern alluvial mode through the propagation of the transients into the South Atlantic convergence zone. Actually, if we want to look at, for example, how the SACS is going to change in the near future, we really need to understand how the ENSO is going to change, how SAM is going to change, how the transient pathway is going to change. And we really need to understand maybe if there is an ocean-atmosphere interaction locally. And that's what I'm going to focus today. Okay? So one of the things that we really need to do, first to simulate it correctly and then to simulate the changes, is capturing the relative importance of each phenomena. And this is quite hard for all models. So just to show you, if you have different trajectories of the transients into the region, this is geopotential height in 200 hectopascals, and the winds are in the arrows. Depending on the trajectories you have of extratropical transients, you're going to have different kind of activity in the South Atlantic convergence zone. And this is well summarized by Leila Carvalho in a series of papers in where she essentially classifies the SACS in 4 types: intense, South Atlantic convergence zone, oceanic. This is OLR, so negative means more convection. So here is an oceanic SICC. Here is a weak SICC because it's positive OLR. And this is continental SICC because the maximum OLR, negative OLR is in the continental region. And associated to each of these types of SICC, you have different behavior of the extremes. Okay, so when you have a weak SICC, you have less extremes than usual. When you have, this is strong, you have more extremes than usual. When you have a weak SICC, you have less extremes than usual. When you have a oceanic SICC, you have more extremes in this region, and so far. So we really need to understand the dynamics of this different behavior of the SICC. And in particular, I'm going to focus on the role of the RC of the role of the ocean in SICC dynamics. And I'm going to show you essentially 2 examples. One is approaching the problem through statistical analysis. I'm going to use complex networks. It's a technique I have been using in the last few years. And the second approach is the regional modeling with RegCM coupled to the ocean, to an MIT ocean model. So let's start with the first one. What are complex networks? Complex networks essentially is a methodology that can be used for any kind of problem, essentially, that all you need is interacting agents. So it can be anything. It can be the internet. This is the internet map. Essentially, you have points. That means you have some computers that are connected to many places. These are called hubs. Okay? And then you can probably find you somewhere here, somewhere in some place. Or you can do also, for example, this is the routes of the planes. So there are some hubs that connect the different cities in the US. So all you need essentially is a set of interacting agents that are connected by any rules. So how do you essentially apply this technique to climate? Well, essentially, the nodes are the agents. So you have the Earth divided in a series of squares. So you can have a time series at each grid point. So on each grid point, essentially one agent. And then, so the nodes are the grid points, and the links, which is how is connected this point to here, essentially the links are going to be obviously related or linked through the dynamics of the atmosphere in this case. So, but you can define similarity or directionality measures that allow you to construct a network of how the atmospheric dynamics works. And the properties of the time series and of the whole globe are contained in the topology of the network. So I want to show you just one example. It's work we did in a few years back, which is the study of the interaction between the ocean and atmosphere in the SICC region using a measure of directionality. Okay, it's not a measure of similarity like correlation, it's a measure of similarity, but not of causality. Okay, we are going to use here Granger causality, which is a measure of directionality. From one point affects the other point. And to do so, in this work, we use daylight interim reanalysis and could quantify the convection. We use vertical velocity at 500 hectopascals, and we use the sea surface temperature to characterize the oceanic state. Okay? And the Granger causality estimator essentially it's a linear model, which is an autoregressive model of some order d. So suppose you have here omega. So you write omega at time t as a function of omega at previous times plus as a function of the sea surface temperature at previous times. Okay, so you have this model, which is an ARD process. And then you do those two things. You fit the model for each grid point, one above each other. So you have the SST here, you have the omega here, and you connect the two points. So you fit the model, and you find the variance of the residuals here, and you call it sigma square coupled. That's when you include both fields in here. And then you do the same, but now suppose here is omega, so you write omega only as a function of omega at previous times, but you do not take into account the SST. And you find the variance of the new model. And you essentially take the difference between the variance of the coupled model and the uncoupled model. And when the variance of the uncoupled model is larger than the coupled model, that's what is called that one variable causes the other one. So it's Granger causal, one variable regarding the other one. You can do a statistical analysis to see when this statistics is significant and so far. But let me show you the results. So you can look at the directions in both ways, from the ocean to the atmosphere and from the atmosphere to the ocean. And here are the plots. This is the plot of the Granger causality estimator. Where it's black is non-significant, where it's purple it's significant. So here it says ocean to atmosphere, and here atmosphere to ocean. So in the SICC region, the main direction of interaction we know is from the atmosphere to the ocean. Okay? The atmosphere forces the ocean. And that's what we recover in here. But if you do the other way around, you can also find that in this region, as well as in the deep tropics, the ocean forces the atmosphere. So there is a two-way interaction there, okay, according to this Granger causality estimator. But we can do one more step and say, okay, this is one point above the other one. Okay, but what happens if I want to know this node, how much is connected to the whole atmosphere above this region? And to do that, what I can compute is what is called the area-weighted connectivity. This is a measure of how much a point is connected to the rest of the points. The larger this value, the more this point is connected to the rest of the points. For example, thinking in the connections of the airplanes, so Houston is a hub. So this region has large area-weighted connectivity. Okay, has lots of connections anywhere. So what you do is essentially you count how many points this point in the ocean to how many points in the atmosphere it is connected to, and you can also tell the direction from the ocean to the atmosphere or from the atmosphere to the ocean. And this is what you have to compute, just a cosine, just to take into account that the areas depends on the latitude. And this is what you find. So when you calculate this non-local connectivity, what you find is that the region of the South Atlantic convergence zone is the region where the oceanic points are most connected to this region in the atmosphere. So these points in the ocean are the points that are most connected with the points in the atmosphere in the direction of ocean forcing the atmosphere. If you look at the regions in the deep tropics, you have to find also a signal there, because we know that in the equatorial region, the ocean forces the atmosphere. Very good. So, yeah, in this work we find essentially that there is a two-way RC coupling in the SACC region on daily timescales. And if you do more analysis, what you find is that in this analysis you find that the RC coupling essentially increases the persistence of the atmospheric anomalies in the region. But now let's move to the sub-seasonal timescales now. Okay, move daily. Now let's move to sub-seasonal timescales within 10 to 90 days timescales. And in 10 to 90 days timescales, the main phenomena that dominates the teleconnections and essentially the dynamics in this region is the MJO. So the Madden-Julian oscillation. And the Madden-Julian oscillation in this cartoon, you know, it's the Madden-Julian oscillation can be thought as a wave propagating along the equator, and once it propagates, essentially helps activating convection in different places of the Earth. So when you activate convection, essentially what you do is you put heat in a place where it used to be, and that essentially creates a Rossby wave sources, and you create Rossby waves propagating to the extratropics to the north and to the south. And this is what is showing in here. So the Madden-Julian oscillation, the MJO, is able to generate anomalies that will affect the South Atlantic convergence zone. It's in a very similar way as the El Niño does to our region. There is also a tropics-tropics connection, essentially that when the MJO is coming this way, it will affect also this region over here. So there have been several studies in the last few years, and to try to understand how the MJO affects South America. And this is one of the first papers by Mariano Alvarez in 2015. And what he shows that we can, following a classification of where the MJO is at each time, you can find what are the teleconnections that the MJO forces into South America for the different phases. So going back in here, so essentially what you say is, okay, when the MJO is in this region, it will tend to generate some kind of Rossby wave. When it moves to this region, it will generate a different one, and so far. So you divide the location of the MJO in 8 places, which is called 8 phases. Okay, and these 8 phases are usually characterized in this diagram, which is called the diagram by William Hendon. And if you, I'm not sure if you see the numbers, it says 1, 2, 3, 4, 5, 6, 7, 8. And according to where it is located, you can define, you can essentially characterize where the MJO is. And depending on the phases, then you can see what are the kind of teleconnections that the MJO generates in the atmosphere. So this is the map for the MJO in phase 1, phase 2, phase 3, phase 4, and then the phase 5 is the same as this one but change sign. Phase 6 is the same as this but change sign. 7 and 8 again the same as these two but change sign. Okay. So this is for December, January, February, which is the season we are interested in. So what happens if you look more regionally? Well, if you look more regionally, the regional impacts of the MJO are described here. Here I put together phases 2 and 3, phases 4 and 5, and phases 6 and 7 of the MJO. So when the MJO is located in certain places of the Earth, for example, I'm not sure if you can see here, but when it's phases 2 and 3, the MJO is in the Indian Ocean. In 4 and 5 is in the maritime continent, and in 6 and 7 in the Western Pacific. That's where the MJO is located as it moves. So this is OLR. So essentially, the MJO shifts the SACC southward. So this is positive OLR. That means that there is less rainfall over here. There is more rainfall over here. So there is less rainfall here in phases 4 and 5. So it tends to shift the SACC southward during particularly phases 2 and 3 and 4 and 5. But it also does something interesting, which is that when you shift here the SACC, okay, there is much more sunshine coming into the ocean. You can see that in the net heat fluxes. This is the positive net heat fluxes into the ocean associated to this decrease in rainfall here. So when you have decreased increased heat fluxes here, essentially a few weeks later, you will have a warming. Because the ocean tends to respond to the increased heat fluxes due to a southward shift of the SACC. Okay? You can see here the positive heat fluxes are in phases 2 and 3 and also in phases 4 and 5, and then essentially die. And this relatively small SST anomaly, it's small but not that small. I wouldn't have expected that much because the MJO moves very fast essentially. And the ocean doesn't have much time to respond. In principle, you have thought, okay, yeah, there is no warming. The anomalies caused regionally by the MJO don't do anything to the ocean because the MJO moves very fast. Okay, but actually it does have an impact in the SST, in the local SST in this region. That tends to persist from phases 4 and 5 to phases 6 and 7. So my question I had in mind is, okay, is there a role for these SST anomalies in modulating the response of the MJO to this region? So what we did is we used the RegCM ES, which is the RegCM coupled to the ocean model. And we first asked, can the RegCM reproduce the signal of the MJO in this region? And the second question we had is there any role for this SST signal? Okay? So here I review a little bit what the RegCM ES is composed of. Essentially, it's the RegCM 4.5 with a resolution of 50 kilometers, 23 vertical levels, and is coupled to the MIT Ocean GCM at the resolution of 1/8, okay, 40 vertical levels. And here's are the domain. The red one here is the atmospheric domain, and the blue one is the oceanic domain. Okay, so the model is coupled only within the blue square. In this region of the ocean, the SSTs are prescribed. So there is no active coupling between the two media. So we performed two runs. One in couple mode, that is the model is presented in this paper. It's a very big collaborative enterprise in the ICTP. I think Erika can vouch for me on that. And but it worked. So the model is there, it's available. And we also, besides doing this couple ocean atmospheric run during 10 years, we also run the RegCM standalone with observed SST. Okay, so there is no coupling. The same region, but with no ocean coupling, just observe SST as a boundary condition of the RegCM. So these are the climatologies of the two models. This is the couple model, the RegCM ES, and this is standalone RegCM. And someone asked yesterday about the double ITCC problem. So here it is. The coupled model has a double ITCC, as most of the global or regional climate models. There is a main ITCC, but there is a secondary maximum here that it shouldn't be there. That is not present when you run the RegCM forced with SST. But both essentially have this South Atlantic convergence zone well defined. There is in the upper Amazon, there is a dry bias in the coupled model that is not really present in the RegCM only experiment. But since we are interested mainly in this region, we say, okay, it's okay. The RegCM coupled to the ocean model has an okay climatology during DJF. And this is the bias in the ocean. The ocean has an SST bias. The bias is that it's much colder here than it should be. It's about 3 degrees or so colder than it should be. And this cooling that you have here is the cooling that divides the ITCC north and south, essentially. So the ITCC is located to the north and located to the south because of this equatorial SST cooling. So how does the RegCM simulate the main patterns of subseasonal variability in this region? So here we calculated the empirical orthogonal functions. This is the leading, the first one. This is for the observed OLR. So it's, again, negative. Here's more precipitation, less precipitation. You have the famous dipole. We know this. And this is for the uncoupled model, and this is for the coupled model. So the coupled model and the uncoupled model are essentially the same, very similar in shape. And they also present this dipole in precipitation. The interesting thing is that if you do the regression of the time series associated with this EOF onto the surface air temperature, you get this. So when you have more rainfall here, you get a cooling in this region, which is expected, which is not really seen in the uncoupled model. Okay, in the SST forced RegCM, you don't see much of that signal, but it somehow appears back in the coupled model. So when you have an increased precipitation here, you have a cooling in this area, this is recovered in the coupled model, but not in the uncoupled model. We don't know that why is the case. We don't know really the reason for that, but at least it shows some improvement over there. So which are the anomalies during the MJO then? Well, the anomalies during the MJO, these are the ones I showed you. This is an OLR. And this is the anomalies in precipitation for the coupled model, and this is the anomalies from precipitation for the atmospheric only model. And I want to stress here one thing, is that the days we use to compute these anomalies are the observed ones, are not the model MJO, essentially, are the observed MJO dates. Okay? So these are directly comparable. So essentially what it's saying is that the model is getting from the boundary conditions the right response into the regional model. Okay? So as you can see, the response in the RegCM is much stronger and somehow more coherent than in the coupled model. You see here a decrease in rainfall and tends to have a shift toward the south, but it definitely is not as strong as in the RegCM, which is closer to what you would find in observations. So the coupled model captures part of it, but not all of it. Okay? Yes? Yes, yes, there is like a displacement here, right? Over the ocean particularly. Yeah, that's essentially the SICC is like broken. And that's actually interesting that happens. In the RegCM, it's essentially continuous pattern of decreased rainfall. But when you couple it, essentially it decouples the ocean from the continental part. Question? And so if you look now at the surface winds, so this is for phase 4 and 5 only. So I took from this picture, I only consider this case, which is where the largest anomalies are seen. So this is the observed. It's not era interim, sorry. This is OLR, NOAA OLR. This is RegCM, and this is RegCM-ES, the couple model and uncoupled model. So this is the same I showed you before. And this is the 10-meter winds for the 3 cases. So this is the observed era interim, pre-analysis era interim winds. This is the coupled 10-meter winds, and this is the uncoupled 10-meter winds. So what is in blue is what is significant, statistical significant. So what you can see is that all of them tend to show this anticyclonic circulation here that is known to be always accompanying a decrease or a southward shift of the SICC. But it's very strong in the RegCM forced model, but it's weaker than the reanalysis in the coupled model. So the coupling is doing something. There is a difference there. What is it doing? We'll see. But if you look at the winds over here, it actually overdoes it. So the RegCM, the standalone RegCM, overdoes the winds in the surface. And this is too weak. So it's something in between is the right response, essentially. So what's the deal here? Well, what we can do is look at to see if the coupled model, in the coupled model, there is a warming here that I should find. You know, in the colors here, I show you the warming that I showed you before that developed during the MJO. It's a forced response to the MJO. And if you look at the coupled model tries to warm, but it doesn't really do it. Okay? This is era interim, and this is the RegCM force with ST. Has the same SST as the observed because I force him with SST, so it's okay. And on top of the colors, you see some essentially some contours, and this is the wind speed. And what you can find is that the wind speed is largest over the warmest waters. Okay? The wind speed is largest over the warmest waters. And if you look at the structure, this is 2 meters per second. This is about the right in size, but a little displaced. And this is about 4 meters per second. So essentially what's happening here, how we interpret these results is the following. It has been shown that the atmosphere can respond to SST anomalies. But how does it respond and why? Essentially, if you have a warm SST with a strong gradient of SST, what you do is that you make the planetary boundary layer less stable or more unstable. And what it does is that you allow the mixing, more mixing in the planetary boundary layer, and that brings horizontal momentum downwards due to the mixing. So when you have warm SST, what happens is that the atmosphere tends to have larger winds on top of the warm SST because you essentially allow more mixing. With the larger mixing, you allow the winds in the free atmosphere to come to the surface. So it's a direct response to the warming that you have a stronger winds in the surface. And this is what is happening in the RegCM standalone. That's why you have so strong winds, because the atmosphere, the local model, is responding very strongly to this SST. So essentially what you have, so if you compare the uncoupled with the coupled model, what you do is that this increase in the winds in the uncoupled model, which is seen here, essentially creates a stronger anticyclonic circulation, which creates stronger convergence toward the south, and that's why you have a stronger shift of the SICC southward. Okay, so but this response in the model is too large when it's uncoupled, but it's too weak when it is coupled because the ocean doesn't really warm up as it should be. So the right response is in the middle. So if I have to somehow interpret these results, is that once once the ocean warms in this region, due to this increase in mixing, vertical mixing, the winds from the free troposphere essentially transfer momentum downwards. You create a stronger convergence, and this helps shifting the SICC southward. And this is the role of this warming in the ocean in modulating the teleconnections coming from the Pacific toward the local region. So going back, and I'm finishing. So the summary essentially is that there is a two-way interaction between the ocean and the atmosphere in the SICC region on daily and on subseasonal timescales. The RegCM, coupled and uncoupled, can capture the MJO teleconnection through the boundaries, particularly the extratropical connection. I didn't talk about the tropical one, talking about the extratropical teleconnection. And the Earth's interaction essentially increases persistence and intensifies the remote forcing from the MJO, inducing a larger local rainfall changes. Just to finalize, let me do some advertising. If you are interested in applying complex networks to climate problems, we wrote a book that is coming soon. It's called Networks in Climate. The co-authors are Henk Dijkstra, Emilio Hernandez Garcia, and Cristina Massocher. And it should be coming in March. Should be out in March. And it's actually, people have used this complex network approach to study extremes, to intercompare models on regional models or global coupled models. So it's a really interesting tool that, that adds new information than besides the usual statistical linear EOFs, SPD, and these kind of things. So thank you.
Thank you, Marcelo. Do you have any questions?
Just a curiosity. We had the same problem with okay, so the things that you are showing, the not warming, but the right wind that you have at the end.
Yes, here.
We had a similar problem in the Indian Ocean Basin, in which we realized that although the wind looked to be okay, but then the temperature and the salinity close to the Bay of Bengal were not correct. And so the gas was that the mixing in the ocean was not the correct one there to reproduce, and can be disconnected to the wrong mixing in the ocean?
Yes, definitely. The way we interpret this, the absence of warming, is that if you look at the bias, you have a large negative bias here. Okay, so essentially what is happening is that during the summer, the ocean stratifies in this region. But this model is not doing that. So it's very hard for the ocean to respond to the atmosphere when you have a deep mix layer. So if it doesn't stratify, so you have a relatively shallow layer, it's going to take much longer for the ocean to respond. And that's what the model is doing wrong.
Okay.
Yeah. So it's a mixing problem, definitely.
Okay. So
yeah.
At least it's wrong in a consistent way.
Yes.
Thank you, Marcelo. I have two questions regarding your causality analysis. There was a figure showing two-way ocean. Yes, that one. Do you think is there any impacts of the time lag to determine particularly for the ocean's atmosphere? What will happen if you use the one day before or the one season before? Did you check? Is there any impact of this to particularly for the ocean to atmosphere impact?
Okay, it's a good question. I didn't dwell into this, but we look here on daily timescales. But if you look at the ARD process, it takes into account the previous days up to a day D. Okay, so when you construct this model, it says, okay, SST at times T, it depends on SST at times T minus several days, 1 week, plus omega at the previous days. And the previous days for omega is about 4 days, and 8D is 8 for SST. So this is essentially some kind of persistent timescales that we had to include into the model to take into account what you are saying on daily timescales. Yes. One issue in this model is to fix this D. You might get different results depending on this. We did a lot of testing and see which scale, essentially, which persistent scale you should take. And these are the ones that show a robust result if you change a little bit the days, 1 or 2 days to each side.
A short one. Did you apply this technique to simplify models? Because we know that no. Okay.
Yeah, you could definitely. Yeah.
Other question? No. Okay. So thank you, Marcelo. Let's go lunch, and so I'll see you in the lab at 2. Directly in the lab at 2? Okay. So tonight we are planning to have some time.
I don't know, maybe Rosemary. Rosemary, do you want to say? No, I know. Yesterday we discussed it with some people here. Tonight you can join in a bar in Vila Madalena. The name is Empanadas. There we have empanadas and beer. But you need to pay your food, your drink, because we don't have money to pay for each one. Okay? It's very easy. Empanadas, Vila Madalena, it's too easy to localize the place. Okay? 8 p.m. Okay? For the people that is in the hotel, it's possible to walk. Yes, to walk from hotel to more or less 5-6 blocks. Eu vou pôr o nome aqui.